Hello, I'm Marco Janssen, professor in school sustainability at Arizona State University. I'm trained as an applied mathematician and work on human environmental systems. In this video, I'll give a brief presentation of an agent-based model I developed with Kim Hill, an anthropologist who is one of the world-leading experts in hunter-gatherer societies. The goal of this talk is to show an example of an agent-based model based on detailed qualitative and quantitative observations. The model will focus on the Ache, an indigenous society in Paraguay, which has been studied by Kim Hill since the late 70s. The presentation will be brief, but if you want to learn more, you can find a publication in Human Ecology, and the model is available in the model library of OpenABM, so try it out. When we started to develop a model of the Ache, our goal was to build a model that captures the knowledge from ethnographic observations, that simulated outcomes that are in line with observations, and is stylized enough so that the model could be used for other cases. We did not just want to simulate the observed patterns. The model should be based on well-developed theory. In fact, the model built on optimal foraging theory, a well-established body of work in behavior ecology. We also hope that the model will allow us to learn something new about the Ache and their foraging strategies. The model we have developed so far is focused on hunting, which generated 80% of the food for the Ache and is only done by adult male. We had access to a large data set of transect data. In the 90s, Ache men were trained to measure various aspects in the park they live in as part of the conservation status they receive. Systematically, they walked through the forest and counted animals they observed, and also noted whether they would hunt the animal if they would be hunting. This valuable information allowed us to calculate the probability a hunter encounter a certain species in a particular vegetation type. We also had access to data of hunting events, how long it took them to hunt during a day, what kind of catches they had, and how long it took them to chase the animal. To capture the detailed information we had, the model consists of 60,000 patches of 1 hectare each and progress in time steps of 5 minutes. This sounds like a lot of data that may cause computational problems, but the patches are only updated every few minutes during a simulation year. Their calculations are mainly to determine the movement of the hunter. In this slide, you see the map of the park where the Ache hunt and which data we use for the simulation. We have 6 different vegetation types, and only on the right you see the location where the Ache have collected data of the encounters with prey that were used to calculate probabilities of the encounters for each vegetation type. This slide shows the same information as the previous slide, but now from the implemented model in NetLogo. One simulated year takes about 1 minute on the standard laptop. These are pictures of some of the prey we included in the model. Most prey have the same availability through the whole year. For each prey, we have information on the average height, encounter rate, pursuit time, success rate, and calories derived from its meat. Each species has its own territory, and this map shows that different species have different levels of encounter rates in different vegetation types. We now describe the basics of the decision-making of the agents. As mentioned before, the simulation progresses at 5-minute time intervals for a duration of about 6 hours a day. At the beginning of the day, they define where the camp will be in the evening. Each camp has 5 hunters representing a group size of 20 individuals, including 5 women and 10 children. We populate a total of 15 hunters on the landscape to represent the pre-European contact density of the population. We explore the consequences of different behavioral assumptions. We started with a random walk of individual hunters. We then had the hunters in 3 camps, but they still were hunting coordinatedly. Then we included coordinated movement of the hunters. In reality, they hunt this way, and we will still be able to see others when they are hunting, but they hunt individually. And then finally, the most complex model, and which is in line with observations, is to include the observation of cooperative hunting for some of the species. For the few species, hunters will call help from each other if they encounter that particular animal. This diagram shows the basic decision of each agent. It first makes a decision where to move to. Once arrived in a new patch, it may encounter an animal. The agent will then decide to hunt the animal or not. If it does, it will take a few time steps before the hunt is over. The hunter has a probability to be successful with the hunt, and if it is successful, an animal is removed from the landscape. This figure shows the relationship between the model and the data on the share of a species of the diet. A perfect model will result in the dots being on the diagonal line. Our model is not perfect, but it's doing a better job than the null model. The null model is basically the relative abundance of animals on the landscape. Adding behavioral complexity leads to a better fit with the data. The cooperative hunting version is depicted in this figure. We did not calibrate the model, but made assumptions on the mechanisms, and more realistic assumptions led to a better fit with the observations. Now we have a model that represents the hunting behavior. We can do some analysis to understand the observed behavior. We varied the group size and the number of days the groups stay in the same place. For each combination, we ran the model about 100 times for 1 year and recorded the average per capita return, the percentage of days without being for food. Note that in bigger groups, people are less likely to be without food since the hunters in a group share with each other. The return of bigger groups go down since big groups going through the forest lead to scaring away the animals for each other. The optimal strategy is to move each day to a new place in the landscape and to have a group size of about 7 hunters per group, which is a group size of 28 people. And this is in line with the observed strategy of the Aceh. So the Aceh seems to find the sweet spot in balancing risk and returns. To conclude, we developed an empirically grounded agent-based model, and we could use this to understand the observed behavior of groups. At the moment, we are developing a more complex model for the case in South Africa, where we built on this particular model. In the South African case, we have no direct observations, since we look at a period between 60,000 and 160,000 years ago. The model includes also more resources, such as shellfish, plants, firewood, and stone material for making tools. Nevertheless, our experience with developing the detailed Aceh model helped us to address the ecological case. Since we have no direct observations, we can use the model to explore the consequences of different behavioral assumptions and compare the archaeological data of bones and stones with the simulated data. Thank you.